we're going to go ahead and talk a little bit about vapor pressure, and hopefully this will make a little more sense when we're all done here. So let's look at this first slide. On the left side, we see some water in a container, and the water has some of the molecules moving from the liquid state into the gaseous state, and some of them are condensing, going from the gaseous state back into the liquid state. And there's an equilibrium there. So over time, some of the water will slowly escape and evaporate. This is a very slow process. On the right side, I've added a cap to the bottle, and what this does is, even though the water is still going from the liquid state to the gas and the gas back to the liquid, it's being trapped in here. And these molecules that are being trapped are going to exert a pressure, and we call that pressure from the vapor pressure. Now, how can this be demonstrated using a U-tube? Well, you can see I've got my U-tube here. I'm going to attach it, and I'm going to add a drop of liquid into the little flask here. And what's going to happen is that liquid is going to volatilize. It's a little hard to see, but you can see there's a little bit of liquid gas in here now. And that gas is now exerting a pressure, and it's actually pushing against the atmosphere up 120 millimeters. So the vapor pressure of that water is not equal to 120 millimeters. It's equal to whatever the atmospheric pressure was pushing down, plus an additional 120 millimeters. So if the atmosphere was pushing down at 760 millimeters of mercury, and then the height difference between these two is 120, then the vapor pressure in the container must be 880 millimeters of mercury. So let's discuss and look at a manometer one more time. So what's going on here is we have two different pressures. We have the atmospheric pressure and we have the gas pressure. And at this point, the atmospheric pressure is pushing down more, causing the liquid to go up toward the lower pressure, the confined gas. And in this case, the atmospheric pressure is less and the gas is pushing more, so the gas pushes down and it causes the atmospheric side to go up. So here we have the gases under high pressure, and then if we just switch that ever so gently, we can get it to switch the other direction. So let's figure out which is, in this first situation, we'll call this manometer A, who's winning the push-a-push war. In other words, is the confined gas or the atmosphere pushing down harder? Well, what you want to be looking at is the height difference. So it's low here, high here. So therefore, the atmospheric pressure must be high and the gas pressure must be less in the atmospheric pressure over here in the bulb. Now, if the height difference between these is 120 millimeters and the atmosphere is 760, let's think about the formula. Big equals small plus height. So the big pressure here must be the 760, so we can add that in. And the height is 120, so if we go big minus height, we'll get the small pressure. So the pressure in the confined gas, in this case, must be 640 millimeters of mercury. Now let's look at this situation. In manometer B, think about who's winning the push-a-push war. Is the pressure in the bulb pushing harder, or is the atmosphere pushing harder? And I hope you agree with me that the pressure in the bulb is pushing harder, so if they started equal, and if the bulb pushes down, it's going to cause this one to go up on the atmosphere. So in this case, the high pressure must be in the bulb, the low pressure is in the atmosphere. And if the height difference is 120 millimeters, we'll still use our same formula, big equals small plus height, but this time we know the small pressure is 760 and we know the height is 120, so the big pressure, the pressure of the confined gas, must be 880 millimeters. In terms of pressure and temperature, you want to understand when I use the term STP, what that refers to. And that refers to standard temperature and pressure. Now, by definition, standard temperature is 0 degrees Celsius in chemistry, or 273 Kelvin. Standard pressure can go by several units. We've seen these units before. 1 atmosphere, which is equivalent to 101,300 kilopascal, or 101.3 kilopascal, and 760 millimeters of mercury. Some older books will call that 760 torr, and that's simply to honor Evangelista Torricelli, the person who came up with the barometer in the 1640s. What equations do we have, or conversion factors that we might want to know? Well, if you're trying to convert from Celsius to Kelvin, simply add 273. If you're trying to get from Kelvin to Celsius, subtract 273. And then finally, we should realize that 1 atmosphere is always equal to 101.3 kilopascal, which is equal to 760 millimeters of mercury. So let's practice conversions. Let's say I have something at 25 degrees Celsius and I want to convert it to Kelvin. Well, that's pretty straightforward. Kelvin is degrees Celsius plus 273. So I take 25 plus 273 and I get my answer, 298 Kelvin. There is no degree sign on Kelvin. It's an absolute scale. Let's try this. How many kilopascals is 1.37 atmosphere? So I'll set up my dimensional analysis. How many x kilopascal is 1.37 atmosphere? I'll use my conversion. Now, if you recall the conversions from the previous page in the bottom, we said 1 atmosphere is equal to 101.3 kilopascal. Atmosphere cancels like that, and we get our answer, 138.8 kilopascal. Let's try one more. How many millimeters of mercury are equivalent to 231.5 kilopascal? Well, we'll write that out. X millimeters of mercury equal 231.5 kilopascal. We're going to use our conversion factor. In this case, 101.3 kilopascal is equal to 760 millimeters. Which one needs to go in the denominator to make that cancel? Good. If you said 101.3 kilopascal, you are correct. 760 millimeters goes in the numerator. Kilopascal cancels like that. Multiply 231.5 times 760 divided by 101.3, and you'll get your answer, 1,737 millimeters of mercury. All right, let's see if we can put some of this to practice here. I have here just the typical setup of a manometer or a U-tube, and the purpose of a manometer is to measure the pressure of a confined gas. You might have one of these in your basement if you live in the Midwest, where we have radon, and it will be attached to that big 6-inch PVC pipe. You always want to see a difference in height, indicating that the air is being pulled out from the basement. If they're equal to each other, it's not working properly. You've got a leak somewhere in your system. So at this point, the two pressures are equivalent inside the gas and the atmosphere because there is no height difference. As soon as the bulb is under higher pressure, notice that the push-a-push war, what happened is where the confined gas is, goes down, and where on the atmosphere side, it went up. Now, if we can tell the difference between those two, we can figure out the pressure. So if we knew the air pressure was, let's say 500 atmospheres, we could convert that, well, it wouldn't be 500 atmospheres, would it? 500 millimeters of mercury, and the height difference was 50 millimeters, then the higher pressure would be 500 plus the 50, or 550. Let's try a problem here. Now, looking at this little setup here, I want to know, first of all, who's winning the push-a-push war? Or phrased differently, where is the higher pressure, inside the confined gas or the atmosphere? What do you think? If you said the bulb has the higher pressure, you're understanding what I'm saying. So now let's work a problem. The atmospheric pressure is 96.5 kilopascal. Is that inside the bulb or up here? Up here, good. Then we're told the mercury height difference is 233 millimeters.
Light on down here.
I'm recording right now. So the height difference between these is 233 millimeters. So next we're told that the we want to find the pressure of the confined gas in atmospheres. Now, because the one pressure is in kilopascal and the other height is in millimeters, and yet the final answer is in atmospheres, we need to make sure everything is in units of atmospheres. So I'm going to go ahead and convert those to atmospheres first. Now, I know I will use this formula, big equal small plus height. We've identified the confined gas as the big pressure, and we've identified the open atmosphere in this example as the small pressure. Now, a rookie mistake would be to simply add up these two pressures and assuming you're going to get the right answer. What mistake have I made? Of course, they don't have the same units, and those units will not add up. So we don't simply want to do that. So instead, let's convert kilopascals to atmospheres. If you recall, there's 101.3 kilopascals in 760 millimeters, or 1 atmosphere. Because we're trying to get to atmosphere, we'll put atmosphere in here. Kilopascal cancels, and 96.5 kilopascal is equivalent to, well, I don't know because I don't have a calculator, but we'll keep moving. Let's now do the 233 millimeters in atmosphere next. So the conversion is 760 millimeters is 1 atmosphere. Millimeters cancel. Now let's do the math on both parts. Okay? So this first part comes out to be 0.953 atmospheres. The second one, if you take the time to put that in your calculator, is 0.307 atmosphere. And if you add those two up, you get the right answer. 1.26 atmospheres is the pressure inside that little bulb here. Well, let's talk a little bit more about vapor pressure before we end this session. So we know that when molecules of gas move, they create pressure as they bump into things. The faster they're moving, the greater the pressure. The molecules, we had talked about intermolecular forces. If molecules want to stick together and stay in the liquid state, they tend to have very low vapor pressures. If they have very weak intermolecular forces, that is, they don't attract one another, when you add any heat, they will escape and they will have a higher vapor pressure. So the higher vapor pressure they have, high vapor pressure, they're going to turn to a gas very quickly, and they're going to have very low intermolecular forces. They're not going to stick together. If they do stick together, they tend to stay in the liquid state longer, they don't vaporize, and they have very low vapor pressures. So let's look at some examples. In this first example, I have water. And water, you'll see, wants to stick together pretty long time because of its what's called hydrogen bonding. That's a type of intermolecular forces. And it will not exert a pressure of 101.3 kilopascal right about here until we get to 100 degrees Celsius. That's its normal boiling point. Ethanol, you can see, reaches that 1 atmosphere point sooner because it boils at a lower temperature or has lower intermolecular forces. And finally, chloroform will boil before any of these other two liquids. So the most volatile substance here is the one that turns to a gas first. You see how this one at the lowest temperature has more of it turn to a gas? That's because it's higher up. All right, we can define boiling as when the vapor pressure pushing up equals the atmospheric pressure pushing down, or the confining pressure. So in this case, if we were to look at these different temperatures, the boiling point of ethanol, when the vapor pressure of ethanol equals the atmospheric pressure 101.3, is 78 degrees Celsius. Water boils at 100 degrees Celsius, and chloroform is going to be far less. Oh, it looks like about 61 degrees Celsius. A little graphic there of some water boiling, showing that right now the liquid is changing into a gas, and it will exert a pressure. If we could capture that gas, we could cause that gas to exert a greater pressure. So, all we're looking at is these little tails or vectors are telling us how fast these water molecules are moving. Notice the ones with the longest tails, they're moving the fastest. Those would be representing the hottest molecules, are going to change from a liquid to a gas first. The one with shorter tails are colder, not moving as fast, and they will stay in the liquid state longer. We're simply looking at here, maybe on the left side, we're heating up a liquid, causing some of the liquid to turn to a gas. And then on the right side, we've reached what's called a thermal equilibrium, where some of the molecules of liquid are turning into a gas, and some of them are going back from a gas into the liquid. And so at this point, we've got a steady state. We've saturated the solution at that particular temperature. And if you've ever been around in the summer when it gets humid, you understand that higher temperature days where there's more moisture in the air can be very miserable to be outside with all that vapor pressure saturating the air. We could boil water on a stove and the water would go away, simply causing evaporation. We're not trapping any of that vapor. If, though, we were to use a pressure cooker, now a pressure cooker is a big, heavy-duty pan. It seals together. Nowadays, most people don't use a pressure cooker like this. They have an Instapot, but this was the precursor to the Instapot that maybe your parents or grandparents would have used. Now, if we look inside there, what's happening, you have water, you start to heat that up. The water would normally want to boil at 100 degrees Celsius, but because that lid is trapped on there, it builds up pressure because the water can't escape, and it gets superheated up to maybe 120 degrees Celsius. And what that means is your food is going to cook at a very fast pace, very fast rate. This is how Colonel Sanders used to cook his chicken in a pressure cooker. And again, you heat that up, and what's happening on the inside is the vapor is going to just superheat up inside here and cause your food to be cooked at a much faster temperature. Hope you have a little bit better understanding of what vapor pressure is, and that when you're using a manometer, you're actually measuring vapor pressure. All right, take care. Have a good day. Bye-bye.